Hey everybody, welcome to the Unit 4 Lecture 1. This is Part 2, following up our discussion on intermolecular forces. We're going to go into the basics of organic chemistry. We're going to introduce how to name, and we're going to look at some properties of these basic organic structures. Now, just to draw a distinction between organic and inorganic chemistry, with organic chemistry, we're dealing with essentially the chemistry of carbon. And with inorganic chemistry, we tend to deal in non-carbon based molecules. We tend to deal in metals based chemistry. So with organic chemistry, we do focus around carbon, but we are going to see a few more atoms show up. We're going to be looking at nitrogen, phosphorus, and sulfur. We will see hydrogen show up pretty regularly, and we will see the halogens show up throughout our lectures. Now, organic chemistry, we tend to deal in low melting point compounds. So in the laboratory, we tend to deal with gases and liquid-based compounds. Many of these are going to be combustible in air, so they require special care when handling. And if you've ever been in an organic chemistry lab or around an organic chemistry lab, they do have a certain scent about them. They have a smell. Now, there's a scientific basis for the smell. We're going to go into the volatility of organic compounds. The more volatile an organic chemical is, the more easily it goes into the gas phase. So we're going to be dealing with chemicals with a scent rather than things like sodium chloride, which you really can't smell when you sit on your kitchen table. Now, carbon is really the core of everything we're going to be doing for the next 4 lectures. It's used for building the scaffolding or building the central structures of all the organic chemicals. Now, carbon has some key characteristics. Carbon is going to make up to 4 bonds. So typically you're going to see carbon making a total of 4 bonds. Now, if we were to rewrite CH3CN so it's a little easier to see, we would see a carbon with these 3 spheres coming off of it. Each one represents an H. And then it's connected to another carbon. This carbon, indicated by the arrow in my drawing here, has 1, 2, 3, 4 bonds. If we look at the carbon next to it, it's got a funny looking bond coming off to its right. It's attached to a nitrogen. It's got 3 bonds going to the nitrogen, and it has 1 bond going to the other carbon for a total of 4. Now, every carbon that we're going to deal with in organic chemistry is going to make a total of 4 bonds, resketching this molecule in the center. The central carbon, one indicated by the arrow, makes 2 bonds to its oxygen and 1 bond to each of the carbons below for a total of 4 bonds that are attached to that carbon. Now we could do this for the remaining carbons, but just keep in mind that a carbon is going to make up to 4 bonds, and we're going to have a distinction between saturated and unsaturated carbons. Saturated carbons are going to only have single bonds. They're holding the maximum number of atoms, the maximum number of hydrogens that they can hold. An unsaturated carbon is going to have at least 1 double or a triple bond. So when I bold this arrow here in the center, the carbon that it's pointing at would be considered unsaturated because it does have the presence of a double bond. Alright, let's jump in. This is going to be our big family of hydrocarbons that we're going to deal with for the day. We're going to learn how to name these. We're going to learn their properties. They're called the alkanes. The alkanes are hydrocarbons, meaning they're composed of hydrogen, and carbons. They're connected all by single bonds, which means saturated. Now, we're going to have to learn some prefixes. These are going to be prefixes that we might be familiar with already. Butane, propane, octane. What do those all have in common? Butane, propane, and octane all end in A and E. That's because they're alkanes, and alkanes ends in A and E also. The difference between butane, propane, and alkane are the number of carbons that they contain. So but and prop and oct are all considered prefixes based on the number of carbons that are in the chain. If you look at the molecules that are at the bottom of the screen, the first has one carbon. The prefix for one carbon is meth, and the ending is ane, so we'd call it methane. Two carbons is eth for the prefix and ane for the ending, so ethane. If we keep going similarly, we'd say propane, and then butane. For 3 and 4 carbons, the prefixes respectively are prop and but. Now you've got a list here. Notice they all end in A and E because they're all alkanes. So what you really need to memorize are the prefixes. 1 for meth, 2 for eth, 3 prop, 4 but, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, and 10 dec. They keep going after that, but these are going to be the most common that we're going to end up using. Now, that aside, we've got a few different ways that we can represent these organic formulas. Let's say we're given a chemical formula, just a plain chemical formula, C4H10. If we were to write this as a structural formula, the first of the three, the structural formula is going to tell us about connectivity. It does not tell us about 3D shape, because if you were to look at the way that this is drawn, it looks like it's a perfectly flat molecule. So it's not telling us how it's arranged three-dimensionally, but it does tell us that this indicated carbon right here is going to be attached to this hydrogen that's above it, and a hydrogen that's below it, and a hydrogen that's left to it, and the neighboring carbon. So knowing connectivity is key also. Now, if we were to move from a structural formula to a condensed formula, I want you guys to look and see if you can tie together the relationship between the two. It still gives connectivity, but by condensing, I'm taking the circled hydrogens in the structural formula and pulling them in to the carbon that they're with. I'm pulling these two hydrogens into the carbon that they're with, and so on throughout the molecule, and it just gives a clearer picture of the overall backbone of the molecule when we have a condensed structural formula. So condensed structural formulas pull the hydrogens in next to the carbons that they're attached to. So let's try drawing one of these for C3H8. Well, the molecule at the top had 4 carbons in a row. We would call that butane. If we have C3, that's going to be propane. And we're going to draw all of our carbons in a row. And think back to how many bonds each carbon needs. Each carbon needs 1 H apiece. To fill up to 4 hydrogens or 4 bonds on every carbon. So the way I've drawn it here, every carbon has 4 bonds coming off of it. So that checks off. That's my structural formula. If I were to rewrite this as the condensed, then every carbon needs to have its hydrogens pulled in next to it. Now if I read this from left to right, the first thing I come across is my hydrogen. So when I write the condensed structural formula, that's why I would write H3, because I come across the H's first to carbon, and then for the remaining I write CH2, 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 CH3. There we go. There's our 1, 2, 3 carbons, and our 3, 4, 5, 6, 7, 8 hydrogens for C3H8. Now there's another way to represent C4H10 and C3H8 in organic chemicals in general, called the skeletal formula, which I do want you guys to be familiar with. Let's do C4H10, the molecule at the top. If I did this in a skeletal format, then I'd start out with a little dot there. That's just my starting point. Now, I can take this let me get my pen back here. And I can draw from that point. 1 to 2, I have 2 points there, to 3, 3 points, to 4 points. Alright, now I've got 4 points, or 4 lines, or 3 line segments that are joined together. If I label these as carbon, 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 and carbon, I've got 4 carbons there. In the skeletal formula, every endpoint and every point where the line disjoints or bends, we're going to show a carbon being there. So I would draw this as 1, 2, 3, 4. I've got 4 carbons in this skeletal formula. For C3H8, I could draw it as 1, 2, 3. 3 carbons there. Now the question is, where did the hydrogens go? Well, this is just an extremely condensed structural formula as opposed to just the condensed structural formula. The skeletal formula only shows where the carbons are. Now, if each one of these 3 dots in this structure is a carbon, ask yourself how many bonds should a carbon have? It should have 4. So if I go back and give each one of these 4 bonds, I can fill in the H's, and in this skeletal formula that I just filled in, this is C3H8. The skeletal formula, though, is just 2 lines shown jointed like that, and every endpoint and every point where lines meet represents a carbon. We'll do a little more practice with this in a bit. Now, skeletal formula for, and because we just did C4H10, let's do a skeletal formula for a new molecule. C6H14. I'm going to start out with a point, and I'm going to go 1, 2. This is 2 carbons. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's my skeletal formula for C6H14. I'm just laying all of the carbons out in a row. We're just dealing with straight chain alkanes right now. Now for C3H8, we've already done that, so let's change it up a bit. Let's do one for C2H6, and let's break this one down a bit. If we started out writing the structural formula for C2H6, we would have carbon attached to carbon, all of our H's to make each carbon up to 4 bonds. There's our structural formula. If we were to condense this, the condensed formula would pull all the H's in next to their carbons, so we would have this. And the skeletal just shows the carbons, so I'm going to have 1 carbon, 2 carbons. This would be our skeletal. And just to make sure we did it right, take a look at this right-hand side right here. This carbon has only 1 bond attached to it. That's the bond running to the other carbon. So to make up to its 4 bonds, it needs 3 hydrogens. Look back over to our structural formula. We had those 3 hydrogens shown. So structural shows all the connectivity, including the hydrogens, everything fully fleshed out. Condensed pulls the H's in next to the carbons. And skeletal just shows the carbons, but doesn't show the letter C. It just shows the skeleton where the carbons reside. Alright, so Alkanes we've treated as these straight chains so far. If you look at the picture in the upper right, we've got our 1, 2, let me change the color of my pen here. We've got 1, 2, 3, 4, 5, 6 carbons, and those 6 carbons are going to form a straight chain. Now, if we wrap those around into a ring, I've still got 6 carbons in that bottom picture, but it's called a cycloalkane. A cycloalkane is in a cycle. Now, we could call it a circle, but that's a little bit of a misnomer because cycloalkanes can look like squares, they can look like triangles. The idea is that they are a closed shape. They're not a straight chain. Instead, they're going to be some form of closed shape like those that I'm drawing right now. Now, if we had to write our formulas for hexane, let's start with a structural formula. Just straight chain hexane, we're going to have 6 carbons all in a row. And every carbon needs 4 bonds, so we fill those in. So bear with me a moment while I fill in all our hydrogens. Alright, there we go. This would be our structural formula. Now, if we take a look at the condensed formula, we would have H3C attached to CH2, 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 CH3. It's our condensed formula, pulling all the H's in next to their carbons. And finally, the skeletal formula, which is the most straightforward to write. We need 6 carbons, so I'm going to start out with 1, 2, 3, 4, 5, 6. That would be my skeletal. And let's not forget where we started with all this. We had just the plain chemical formula, which gave the ratio of all the atoms. I had 6 carbons. If you count on this picture, the darkened spheres I have 6 of, and the lighter spheres represent the hydrogens. I've got 14 of those. So really 4 representations. I've got a chemical structure, I've got the structural formula, I've got the condensed formula, and I've got the skeletal formula. Let's do the same thing for cyclohexane. Cyclo means we're no longer dealing in a straight chain, we're dealing in a ring. So if you count up all the dark spheres, I've got 6. If you count up all the light spheres, I've got a pair on each carbon, so that's C6H12. When we looked at the straight chain version, it was C6H14. So for the same number of carbons, the cyclo version, the ring version, has 2 less hydrogens attached. So we've got our chemical formula here. Now, we've got 3 left to write. We've got our structural formula, we've got our condensed formula, and our skeletal formula. Let's start with our structural formula. Now I've got a ring that I'm going to draw as a hexagon because I've got 6 carbons that are attached. To each carbon, if you look at the picture, I have 2 hydrogens. So let's fill those in here. This would be my structural formula for my cycloalkane cyclohexane. Alright, now let's do the condensed formula. I'm again going to start out by writing out my hexagon, because we've got a 6-sided ring. And then I'm going to put the hydrogens directly in next to the carbons. Because we're dealing with a condensed structure. Now, I want you to pause the video and write what you think the skeletal structure should look like, keeping in mind that the skeletal structure doesn't show the hydrogens, it just shows where the carbons are. Alright, so let's resume. We've got 6 carbons that are in a ring, so I'm going to start here. I'm going to go 1, 2, 2, here's my second carbon, to 3, to 4, to 5, to 6, and then I'm going to close off my structure there. 6 carbons. So this would be my skeletal structure. Alright, now we have covered 2 types of alkanes, straight chain alkanes, and we've also covered cycloalkanes, but we can have branched alkanes as well. Now, let's look at the chemical formulas for the 2 structures that are below here. The left structure has 4 carbons, and when you count up the hydrogens, I've got H10. If you look at the structure on the right, again I have 4 carbons, and I have 3 hydrogens here, 3 hydrogens here, 3 here, and one last one here. I have H10. Now, they have the same chemical formula, but a different arrangement. One is in a straight chain and one is branched. The left would be considered a straight chain. The right would be considered branched. Now, between the two, same chemical formula. If we were to write out the skeletal structures for these, the left would have 1, 2, 3, 4. The right would have this. So, we need to be able to distinguish between the two with our naming schemes, because one of the next steps is going to be to name these chemical formulas. Now, step 1 in naming is to pick the longest chain of uninterrupted carbons that you can put your pen down and trace all the way through the molecule without hitting that same carbon twice. So, if I look at this carbon here, in that molecule, I can trace 4 carbons. Now, after I have circled the longest chain of carbon atoms, the other name for that is the parent chain, I need to look at what's hanging off. Well, on this side, I've got an H. But H's are everywhere in organic chemistry. We're not worried about naming our H's, so we're going to disregard that hydrogen. But we are going to look at this group that dangles below. We've got a CH3. It's a carbon group. So I will be naming that group based on the number of carbons. It has 1C. So let's look up our prefixes for 1 carbon and for 4 carbons. Going back to our list of prefixes, 4 is going to be bute. 1 is going to be meth. So we've got meth for 1 and bute for 4. Let's head back to where we were. Give it a moment to load here. Alright, so the name of the parent chain, because it's 4 carbons long, is going to be butane. This is going to end up working like an address, stating what's hanging off of butane and where it's hanging off of butane. So when asking what is hanging off of butane, we would say a methyl group is hanging off. When we talk about a small group hanging off of a large chain, instead of saying methane, we would say methyl, or propyl, or ethyl, or butyl. It ends in YL. So methyl is what's hanging off. So what's hanging, and it's hanging off of a butane. So this is always the order that things go in. What's hanging off is listed first in the name, and at the very end of the name, the parent chain goes there. So now we have to specify where this methyl group, or one carbon group, is hanging off. And we want to give it the lowest position number that we can possibly give it. So I could name these 1, 2, and I'm numbering the carbons in my parent chain, 3, and 4. Or I could number it going from the other side, 1, 2, 3, 4. If I number from left to right, the top numbers, my methyl group is hanging off of that second carbon. If I number from right to left using the bottom numbers, that methyl group would be hanging off of the third carbon. We want to give it the lowest position number that we can, so we're going to say it's hanging off of the second carbon and number from left to right. You have the choice to number it going left to right or right to left. Always choose so that your position number is the lowest for what's hanging off of your parent chain. So we'd call that 2-methylbutane. 2 because the carbon is hanging off of the second carbon in our chain. Methyl because we've got a 1-carbon group hanging off. And butane because we've got a 4-carbon parent chain, or the longest chain that we could trace in the molecule was 4 carbons long. So let's get a little practice in this. Let's start on the upper left molecule. Now, this is a special case. This is a cycloalkane. When naming cycloalkanes, the parent chain is easier to spot. The parent chain is the circle. The parent chain is the cycle. So count how many carbons I've got in that ring. I've got 4. So we would call this parent chain cyclobutane. And let's look what's hanging off. I've got 1, I've got 2, I've got 2 groups hanging off, and each group has 1 carbon attached. Our prefix for 1 was methyl, but I have 2 of them, so I'm going to call that dimethyl. So going in order, we should say what's hanging off. Dimethyl is hanging off. I have 2 methyl groups. And what is it hanging off of? It's hanging off of a cyclo, because it's in a cycle, butane. Now we have to specify where it's hanging off. Now on a ring, you can start counting anywhere. And you want to start counting so that we can give our molecules the very lowest set of position numbers that we can possibly give them. So if I start on the upper left, I've got 1 and 2. I could start on the upper right also and get the exact same set of position numbers, and those are the lowest that we're going to get. Other possible position numbers would be 3 and 4, but again we want the lowest set, so we would name this 1, 2, dimethylcyclobutane. That was kind of a mouthful. Now we'll get to a few more examples of these, but what I want to point out in this one is that we had 2 methyl groups hanging off, so we had to call it dimethyl. So 2 of the same group, we use the prefix di. 3, we would use tri. 4, we would use tetra. And let's leave it at that because we won't go anywhere past tetra, and we'll tend to stay in the di and tri region if we have more than one. All right, let's jump into example number 2. Example number 2 is a ring again, but we've expanded the ring a bit. If you trace all the way around the ring, and remember the parent chain in the ring is the ring itself. And in that ring, I have 5 carbons. So I'm going to call it cyclopentane. And what do I have hanging off the ring? What's not circled at the moment is a single CH3 group. It's a 1 carbon, so it's a methyl group. So methyl cyclopentane. And the very last thing to note is where it's hanging off in the ring. Now we could start numbering on any carbon that's in this ring. We could number clockwise, we could number counterclockwise, that's entirely up to you. But the best way to number this ring is to start on the carbon where our methyl group is hanging off and just label it 1. So I would say 1 methyl cyclopentane, or better yet, if we just wrote methyl cyclopentane, it's just understood that that methyl group is coming off of the 1 position. This is really the only time you can leave off position numbers. If you have a ring and your group is coming off of just 1 position and you only have 1 group. Now, let's hit up number 3. Pause the video and see if you can circle the parent chain, the longest uninterrupted number of carbons that you can circle with your pen. Alright, now the parent chain that I see could either go like this, or could go straight across. Either way, we've got 6 carbons in the group. Good job if you selected either one of those parent chains. So 6 carbons is going to make this hexane. We're leaving off cyclo because we no longer have a ring structure, we just have a straight chain structure. And let's see what's hanging off of it. I'm going to take my parent chain to be on the bottom here. So what's hanging off of it is this group up top. It's a 1 carbon group that we can call a methyl group. So we've got methyl, or what's hanging off, hexane, which is the parent chain, so we'll call it methyl hexane. And then we have to number our carbons. Now you number the parent chain. If I number from left to right, then my methyl group is coming off of the 2nd carbon. If I number from right to left, it's coming off of the 5th carbon. We want the lowest position number, so I'm going to number left to right on my parent chain and say my methyl group comes off of the 2nd position. So we would call this 2-methyl hexane. Alright, this is getting a little bit uglier, but it's still very doable. Pause the video for a moment and try to select the longest chain of uninterrupted carbons that you can trace with your pen on that left structure. Alright, let's break out a highlighter. Now, what I'm seeing for the longest chain of carbons that we have available is going to start on the right hand side, so it's going to move 1, 2, 3, 4 carbons so far, 5, 6. Now at this point we could go up or we could go left, and either way we're going to end up with 2 more carbons on our parent chain. So I'm going to go to the left here. So there's our parent chain. 1, 2, 3, 4, 5, 6, 7, 8 carbons attached. So if you look back at your list of prefixes, which I would make flashcards for because those are key in naming, we've got 8 carbons, so my parent chain is going to be octane. Not cyclooctane because it's not in a ring, just plain old octane. Now, notice we got a pattern here. Every one of these examples, we've been finding out what the parent is, and then name it. We've got octane. Then we've looked at what's hanging off. Here, I've got 2 groups, and each group has 2 carbons. The prefix for 2 is eth, so we would call this ethyl groups, but I've got 2 of them, so I'd call it diethyl. So now we put it all together. I've got diethyl octane. What's the very last thing we need to do? We've got our parent chain, we've got our substituents, and they're all put together in a name. The last thing we're missing is position numbers. Now going left to right, I could go 1, 2, 3, 4, 5, 6, 7, 8. Or going right to left, I could go 1, 2, 3, 4, 5, 6, 7, 8. Numbering left to right gives me 3, 4. Going right to left gives me 5, 6. So I'm going to take the lower set of position numbers and number from the left-hand side to the right-hand side and give the position numbers 3, 4, diethyl octane. So there's our name for that molecule. Alright, this is a little early in the naming game, but go ahead and pause the video and try to name the molecule that's on the right-hand side. Alright, let's start back. The first step in all of these is identifying the parent chain. In a cycloalkane, or an alkane that's shaped in a ring, the ring itself is the parent. So I've got 6 carbons in my ring, and it is a ring structure, so I'm going to say cyclohex because I have 6 carbons, ane, cyclohexane. I'm going to go through and circle the groups that I have. I have a pair of groups, one here and one here, that both have 2 carbons. So I have 2 carbon groups, so we'll call them ethyl groups, and I've got 2 of those type of groups, so we'll say diethyl groups because I have 2 groups that each have 2 carbons. So putting that together, I've got diethyl cyclohexane. Alright, numbering. It's best to start numbering where you've got something hanging off of the ring, so I could number this 1, 2, 3, going counterclockwise around the ring. That would give me position numbers of 1 and 3. Or I could number this 1, going clockwise, 2, 3. Doesn't seem to make a difference because either way I get position numbers of 1 and 3. So my name for this molecule is going to be 1, 3. Notice the numbers are separated by a comma, dash, diethyl cyclohexane. Alright, we're going to have a few more substituents to add. We've looked at groups hanging off, or substituents, of carbon groups. We've had a 1 carbon group that's a methyl. We've had a 2 carbon group that's been an ethyl. But we're going to add the F that could be hanging off. That would be called fluoro. Make sure you spell it right so it's not fluoro. We could have Cl hanging off, and that would be a chloro. Br is bromo. And the odd sounding one I is going to be iodo. Alright, so starting on number 6. First step is always parent chain. So longest chain of carbons that we can trace with our pen without lifting up our pen or hitting a carbon twice is 4 carbons. prefix for 4 is but, so we'd call this butane. Not cyclobutane because we're not in a ring, we're just in a chain. And circling everything except the hydrogens that's hanging off, that's not included in the chain. I've got 2 BRs that are hanging off. The name of a BR group is bromo, and I have 2 of them, so I'm going to call it dibromo. And if we number left to right, I'd get 3, 4 for my positions for my bromos. If I number from right to left, I would get 1, 2. So we're going to go with 1, 2, dibromo, butane. And just like a street address, it says the parent chain, what's hanging off of the parent chain, and where it's hanging off of. Instead of city, state, and street, we have parent chain, what's hanging off, and where it's hanging off, just like an address. Now, let's tackle number 7, since we've got number 6 named. Parent chain is 3 carbons. We haven't come across a 3 carbon yet. And I've got 1 I group that's hanging off of it. So my parent chain is in a cycle, so we're going to call it cyclo, and the prefix for 3 is prop, so cyclopropane, cyclopropane. And then since I only have 1 group hanging off in a ring, you can choose anywhere to start, so I'm going to name this the number 1. So it's an iodo group, so iodo cyclopropane, all one word. There's a little space here, but we could fill it in. It's iodocyclopropane. We could call it 1 iodocyclopropane, but remember, this is a case we have 1 item hanging off of the ring, 1 group, and it's hanging off in the first position, so that can be assumed. We can just write iodocyclopropane. Alright, now, it says alcohols are the next to name at the top here. We're going to skip the alcohols. We're going to stick with naming these halogens, the bromo groups, the chloro groups, and so on, and maybe throw in one just for practice that's just a hydrocarbon. So name this. Number 8. Pause the video. The steps that you want to do are name the parent chain. 2. ID the substituents or groups hanging off. And finally, number 3, give position numbers. Alright, so step 1, parent chain. 3 carbons. And we have to ID substituents next, and I see nothing hanging off other than hydrogens, and we don't have to name hydrogens. So, my parent being 3 carbons long, prefix is prop, ending is ane. I've got propane here. And since I don't have anything hanging off, I don't have to worry about naming substituents or giving position numbers. This is just propane. Alright, let's tackle number 9. Parent chain first. I've circled there. And it looks to me like we've got 2 groups that are hanging off. I've got 1, 2, 3, 4, 5, 6 carbons in my group. And we would call these, because it's 6 carbons, hexane. Because hex is the prefix for 6. And I've got 2 chloro groups. So I would say dichloro. Oop, that's not showing up there very well. Dichloro, because of the 2 chloro groups. And now we have to decide on position numbers. So I've got 1, I've got 2, 3, 4, 5, and 6. If I number from right to left. If I number left to right, I get 1, 2, 3, 4, 3, 4, 5, 6. So in numbering left to right, I get position numbers of 2, 5. In numbering from right to left, I get position numbers of 2 and 5. So it doesn't matter in this case which direction that I number in, I still get the numbers 2 and 5. So really it's up to you which way that you number. So I'm going to label this as 2, 5. And that's going to be dichloro, hexane. And there's our name for number 9. Alright, light at the end of the tunnel here. Get a little bit of extra practice in. So, I'd like you to pause the video again and attempt numbers 10 and 11, and then we'll go through the answers. Alright, number 10. I've got 3 carbons that are in my ring here, and they're in a ring, so I'm going to call it cyclo. And what's the prefix for 3? Prop. Ane is going to end it because we've got an alkane. Now, the next question, because this is the parent, would be what's hanging off? We have no substituents in number 10. So all I have is the parent chain. So I'm going to call this cyclopropane. If we do the same thing for number 11, I've got the parent chain circled here. I've got 4 carbons in it, and it's in a ring. So cyclo, due to the fact that it's in a ring. Bute, because I've got 4 carbons. And ane, because it's an alkane. I have nothing hanging off of that ring but hydrogens, so I don't have to name or number any substituents, so it's just plain old cyclobutane. Alright, kicking it up just a notch. We'll do these together. We've got to be able to pick out our main chain or parent chain, and then ID substituents that are hanging off. 1, 2, 3. Try counting in a few different directions just to see what the longest chain is that you can identify. Now, the longest chain that I can identify in this molecule in number 12 follows this path. That I've indicated here. I've got 2 substituents coming off of this, one in each of the circled areas. This is the first time we've come across one of these where I have 2 different substituents hanging off of the same parent chain. I've got 1, 2, 3, 4, 5, 6, 7 carbons in my parent chain. It's not in a ring, so I'll call it heptane. No need for the cyclo. So heptane is my parent. I've got a group with 1 carbon. I'll call that a methyl group. And I've got a group with 2 carbons. We'll call that an ethyl group. And now we've got our parent, we've got our substituents named, and we have to decide where things are going to go. If I number from left to right, And my position numbers are going to be 1, 2, 3, 4 for the ethyl, and for the methyl it would be 5. Now this is if I go left to right. If I go right to left, I would end up with 1, 2, 3 for the methyl group. And let's see what we get for the ethyl group. 1, 2, 3, 4 for the ethyl group. Now the best option here is to go with the lowest set of position numbers, so I'm going to go with the 3 and the 4. The question is, how do we put everything together? We put position number and then name of the group, and then we work our way to the parent chain. But because we have two different substituents, we've got ethyl and methyl, we're going to need to put them alphabetically into the name. Now if we had di or tri or tetra, that doesn't work its way into the alphabetical ordering, but we've just got one of each, so we could say that E comes before M in the alphabet, eth comes before meth, so we would say for ethyl, three methyl, and then our parent chain, heptane. No spaces anywhere in the name. There we go. That's our name. That was a good challenger. Let's do one last one. This is similar to number 12 in the sense that we have two different types of substituents. But here we've got a ring, so we don't have to think to choose the parent chain. The parent chain is just the ring. That's all it's going to be whenever you have a cycloalkane. So with 6 carbons in our ring, we could call this cyclohexane. And off of my ring, I have a 1 carbon group, which is a methyl group. That ul ending because it's hanging off. I've got a 2 carbon group. We'll call it an ethyl group. Eth because we have 2 carbons in it. And now we have to decide how to name. Going bottom to top, I could start here at the indicated 1, and I could go up this way. That would give me position numbers of 1 and 3. Or I could start at the top and work my way down, and still I would get position numbers of 1 and 3. The difference here is I need to go alphabetically, because it doesn't matter if I start at the top or if I start at the bottom. Then I need to make the choice that gives it an alphabetical order. E comes before M in the alphabet. So if it doesn't matter as far as lowering my position numbers, I can go in ABC order and give the ethyl the 1 position and the methyl the 3 position. So ethyl comes first in the name because it's first in the alphabet. 1 ethyl, 3 methyl, cyclohexane would be the name of this chemical. Alright, let's pause for a moment and take a little breather and stretch your legs, grab a drink. Alright, welcome back from your breather. Now, let's go through some of the properties. We can name them, we know the general structural properties, we can write chemical and structural and condensed and skeletal formulas, but just the properties of the chemicals themselves. If we look at alkanes, and we just have a general alkane molecule, they're nonpolar, which means what we don't have is a negative side and a positive side. Those aren't going to show up in our alkanes. Instead, alkanes have no negative and positive side. They don't have dipole-dipole forces, they don't have ionic, and they don't have hydrogen bonding unless they're functionalized. So what we're going to have in plain alkanes is dispersion forces. If you think back to part 1 of this lecture, dispersion forces were the very weakest forces that we had of the 4 forces. So that means the molecules of alkanes are not held very tightly together. They're held very weakly together. Now, there's a phrase called like dissolves like. So things with similar intermolecular forces are going to interact better with things that have similar intermolecular forces. Water is H2O. Water had a special type of intermolecular force because it had an H directly connected to an O. We said that it could H bond. Now, because of this, because water can H bond, and oils and alkanes tend to have dispersion forces, they don't have like intermolecular forces, so they're not going to mix very well. Think Italian salad dressing. Italian salad dressing is an oil, and alkanes tend to be oily mixed with water. Now, Italian salad dressing layers out. You get a water layer, you get an oil layer, but they don't mix because they do not have like intermolecular forces. And in a bottle of Italian salad dressing, you tend to see, with those two layers, the H2O or water layer shows up on the bottom. The oil layer, or the alkane as we can think of it, layer shows up on the top. Now, with those two different layers, we can show that oil floats above water. Oil tends to have lower densities, which is part of the problem with oil spills. The oil is going to thin out and form a sheen above the surface of the water. Makes it very difficult to collect. And, well, one thing we do have going for us, though, is the immiscibility with water. Because oil doesn't mix with water and dissolve in water, makes it a little easier to skim across the top. There are a lot of new skimming technologies that they're using for oil spills to help contain them. Alright, general properties as a function of number of carbons. This tank over here to the left, we've got a propane tank. Propane, 3 carbons. Working our way to the right, we've got gasoline, or octane at 8 carbons. Jet fuel, 10 to 14. We work our way to paraffin wax. We're talking around 30-ish. And then up to Crisco, which we're going to think of in terms of around 50 plus carbons. Now, these are the number of carbons in their molecules, the number of carbons in their chains. And as the number of carbons goes up, what you see is a transition from initially where we have a gas, it goes through the liquid state. See if we can get this to spell out here. Liquid. And we go all the way up to Crisco, or vegetable shortening, which is in the solid state. Now it gets more and more and more dense as the number of carbons goes up. Now, because they're nonpolar, they're held together by very weak dispersion forces. Alkanes tend to melt very easily. They tend to boil very easily. So at room temperature, most alkanes are going to be liquid and gaseous unless we get up into the very high molecular weights with many carbons, where we get into the waxes. Now, substances with low boiling points we call volatile. Volatility, or being volatile, means a substance will go into the gas phase very easily. Now, we said alkanes are nonpolar, they're held together very weakly. That means they're going to pass from the liquid state to the gas phase very easily. Now we have an order here of boiling points from high to low. The cycloalkanes tend to have higher boiling points than the straight chain alkanes. So we can sketch out a ring here being higher than a straight chain, so higher than this, which are going to be higher than something that is branched. Like that you would see below where it's written branched. Alright, alkanes are also known for undergoing combustion reactions. Think of some things that we use for fuel. We use octane in our cars. We use butane in our lighters. We use propane and lighter gas molecules in our gas grills. Now, combustion is a general process we did cover previously. It involves a fuel which changes depending on what's being burned or what's being combusted. We're going to add oxygen gas. This is key. No oxygen, no combustion. That's going to go to combustion products of carbon dioxide and H2O. So, in recognizing a combustion reaction, we tend to have an alkane as a fuel that we're going to be looking at, and oxygen. Those are the two reactants that are required for the process to occur. And the two products we're looking at are CO2 and H2O. Alright, we had alkanes, but we have two similar families, they're closely related, called the alkenes and the alkynes. If you see at least one or more double bonds in an organic hydrocarbon structure, that's going to make it an alkene. If you see one or more triple bonds, you're going to have an alkyne. So, given something like this, for a skeletal structure, this would have all single bonds, so we would call it an alkane. But if we slightly modify that structure to give it a double bond, this is now considered an alkene. And triple bonds work the same way. If you see a triple bond that supersedes all others, we're going to call it an alkyne. So given a skeletal structure like this, we might call it an alkane, but given a skeletal structure which has at least one triple bond, is going to make it into an alkyne, like the one shown to the right here that was just sketched. Now, with a double bond, we see something pop up that we did not have in single bonds, and that's the issue of cis, or same, versus trans, which we're going to take as opposite. So if we look at the two alkenes written above, I've got one on the left and I've got one on the right. There's a difference between the two. Take a moment and look at the difference. Here, I've got my double bond in each. So if we draw an imaginary line along the length of that double bond, we end up with something like this. Now just focusing on this left molecule for a moment, the cis molecule. Now we drew a little wall along the double bond. The two large groups that are coming off of that double bond are on the same side. So we consider this cis, or same side. If you look at the trans molecule, the molecule to the right, we drew that same little wall in along the length of the double bond, and the big groups, the CH3 groups, are on opposite sides. That's why we're looking at trans here. Now, leaving that aside for a moment, we have a few reactions to go through. 3 that we're going to start with now, and 1 that we'll introduce in later lectures. We've got hydration, halogenation, and hydrogenation. When you think hydrate, what do you think? Maybe Gatorade, maybe drinking water. It's because a hydration reaction is going to react water with an alkene. These are all examples of alkene-based reactions. So on the left here, I've got my double bond, which makes this chemical an alkene, and I've got a water. Now what happens here in going from where I start to where I finish is I'm going to take this water molecule and I essentially split it into 2 parts. I split it into an OH and I split it into an H. Now on the alkene, where I started out with a double bond, we're going to take away that double bond. That leaves room for me to put the OH on one carbon and the H on the other carbon. So if I take my OH and I attach it to this bottom carbon here, and my H and I attach it to this top carbon here, I'm going to get out this structure right here. So step 1 is remove the double bond. So what I'm scratching out right now. Step 2 is to add an H in one position and the OH in the other position. And we end up with the product of a hydration reaction. For halogenation, very similar concept. I'm going to go from an alkene to adding 2 atoms of a halogen. I start out with a diatomic. This X2 could be Br2, it could be I2, it could be Cl2, it could be F2. They can undergo halogenation, or I'm adding halogens to this alkene. I'm going to get rid of the double bond, and in each position where that double bond used to be, I'm going to add 1/2 of my diatomic molecule. So if it were Br2, I would be adding a Br in each position. But notice when we're done, that double bond is gone, and it's just a single bond now. And on either side, on each carbon, where that double bond used to be, I've got a halogen added in their place. That's what constitutes a halogenation reaction. Okay, last I've got a hydrogenation reaction, which works the exact same way as a halogenation reaction. I start out with an alkene, and in going from here to here, I've gotten rid of this double bond and just made it a single bond. I've split the hydrogen diatomic molecule in half, and I've added 1 to each side of where the double bond used to be. So the same general process for all 3 reactions. To the right, this is shown as a catalyzed reaction, meaning that this reaction has been sped up, and it's been sped up by the presence of a metal surface. Now, a reactive metal surface can speed up a reaction like a hydrogenation reaction because the H2 gas, the hydrogen, can deposit itself on the metal surface. When it does so, that can facilitate the splitting of that H2 into individual H's. The alkene comes in from above, and it can pick up those two H's and form the product that we got in our hydrogenation reaction. So thinking back, we introduced the ideas of cis and trans. Cis meaning same side, trans meaning opposite sides. The top molecule, let me change my pen color here. The top molecule represents a cis molecule. So our double bond shows up here. Actually, that isn't showing up very well, so let's pick a different one down here. Seeing as that is the same side, we see a bend in the molecule. And that bend is brought about by the presence of the alkene bond. And being cis, the long chains are going on either side of that alkene bond, producing a kink in the chain. So we end up seeing this bend in the chain for a cis fat that we don't see in a trans fat, because the double bond in a trans fat molecule allows for that chain to stay relatively straight all the way across. Now, the difference in the way that these fats pack makes a difference in the way that our body interacts with them. I want you to think of a bundle of cis fats. Cis fats aren't going to pack very well compared to trans fats. Cis fats have these kinks in them that are brought about by the double bonds that are in the cis fats. But when we have trans fats, because they're relatively straight, they're going to pack very, very, very well. So when you think of artery clogging capability, trans fats are going to be a little more solid when they pack than cis fats because of all the kinks in their chains. Now I've included a video or two at the end that you can look up next to the link for this video to look at the differences between cis and trans fats and some of the health effects and some of the movements that are being made to limit the trans fats in our diets. Now we're going to wrap things up with polymers. Polymers are made up of monomers. Monomers are repeating chains. They're units which build up a polymer. Let's say my monomer was a circle. If I built a chain from these identical circles, I would be building a polymer. Polymer means many mers. Monomer means one mer, or one unit. So one building block, or the circle that I'm building, represents a monomer, and once we get up to many in a chain, we would call this a polymer. So we have simple polymers up to very complex polymers, but they all have something in common, and that's that they have a repeating structure. Now, if we can identify the repeating structure inside the polymer, like the one listed as number 7, we can identify the monomer in this chain. If I take this piece that I've bracketed here and I repeat it over and over and over again, I'm going to get out the polymer that's shown here. So I would consider this piece that I boxed the monomer. That's one thing I would like you guys to be able to identify here, is the smallest piece that you could repeat to get out the polymer. There's some practice on this listed on Blackboard under the practice homework. Molecule listed on the right here has brackets here, one here, and it says everything in that bracket is the monomer. So this piece here represents the monomer, and this N on the outside means we repeat that monomer as many times as we need. N could be 10. That would mean we'd have 10 monomers. It could be 1,000. That would mean we have 1,000 monomers all in a chain making up our polymer. But this is the simplest repeating unit, and it's polystyrene. This is the foam that you would tend to see in coolers. It's the foam that you used to see in packing peanuts. Alright, and finally, we have polymer number 2 down here. It's listed as high density polyethylene, HDPE. This is a very, very common polymer to see in materials that we use every day. Now let's pick apart the name a bit. HDPE, the E is what I'm most interested in. Ethylene. What did our eth prefix mean? 2 carbons. So we can start to tie the naming scheme that we're used to into something we can use with things that are more complex. This is high density polyethylene, or many 2 carbon groups. This would be our monomer, and the N again signifies we have as many as we need there to make up our polymer. So pieces I would want you to take from this is to be able to identify a monomer given a picture of the polymer chain. Know your definitions of monomer and polymer. And that's about it for polymers there. Now I have an exercise for you guys. I posted the link on Blackboard. This is something you can do for fun in your own time. But it takes glue, Elmer's glue, which is made up of polymer chains. And it also takes borax, which is a type of soap which you can find in the laundry detergent section of your grocery store. Now you can do this experiment for under $2, so if it's something you're interested in trying, go for it. But you're taking these long polymer chains, which is the glue, and you're making connections between the chains. Think about what's going to happen here if I tie all my chains together. Think of a plate of spaghetti. If I have a plate of spaghetti, it's a bundle of noodles. Would it be easy to eat or hard to eat if I tied all the noodles together? It would be hard to eat if I stuck my fork into this pile of spaghetti and all the noodles were tied together. When I brought a bite up to my mouth, I would bring all the noodles up when I lifted my fork. But if all the noodles were loose, I might bring up a single noodle when I dug my fork in and tried to bring it up to my mouth. So we see a different behavior out of a polymer if we can tie these strands together. These strands are called crosslinks, and these crosslinks between polymer chains are going to make them more rigid. So in taking glue, we could consider glue rather liquidy. You can pour it. But when the glue meets the borax, you cross-link all the glue strands together, and you end up with something that's more like a putty, like a silly putty, or a gack, or a goo. So something fun to do on your own time. There's a YouTube video, but also written instructions on how to do this. Alright, thanks for being around for Unit 4, Lecture 1, Part 2. Continue on with Unit 4, Lecture 2 whenever you're ready.